Matteo Guainazzi. I have been working since 15 years ago in science operation of the XMM Newton spacecraft, and I am in this moment, since a couple of years, I am a calibration scientist. And I would like to thank Michel and Alessandra for inviting me, and they gave me the slightly unusual, and for sure as fast as I can remember, unprecedented task to provide you with some insight of our current limits on knowledge of X-ray astronomy measurements deriving from problems in instrumentation, or better stated, problems in calibration, instrumentation calibration. I am personally not an instrumentalist. I have an astronomical background, although I have been working in calibration for some years. So I've tried to approach this topic from a user perspective, from a scientific perspective. So I hope I will skip any uninteresting technical details and go directly into what the data tell us in this sense. So let me first start reviewing a well-known results, which was published 1 year ago, more or less. Bennett et al. Made an interesting experiment with fishes, with a special type of fish, salmons, I think. And I apologize with the chair and my Roman colleagues, they already know the story. And basically what they did is actually very exciting. They took this fish and they connected some sensors in the brain of the fish, and they showed to this fish pictures of human beings, both male and female, in different states. So happy state, sad states, faces of human being crying, faces of human being laughing. And they were measuring the reaction of the brain to being exposed to these pictures. And they made maps of the brain, and depending on which picture was shown, they noticed that the brain, different parts of the brains were activated. And that's very exciting because this is the first proof that fishes can actually understand and feel human beings. So empathy in living beings apart from humans. They describe actually the experiment set up in great detail, and one interesting point is that this fish at the time of the experiment was dead. Was as dead as a dead parrot in the famous sketch of the Monty Python, for those of you who remember. And this is not a joke. I find this as an extraordinary piece of work, which actually was awarded with the Ig Nobel Prize last year. And it's essentially a paper on systematic errors. What these persons, these colleagues are criticizing in their community is that there is very little attention in their community of ensuring a reproducibility of the results. So there is basically no way in this community to control the systematic error on the measurements. So what they were measuring with these brain pictures were essentially the systematic error of their instrument. So the outline of my talk is to try and show which is our dead fish. And I will show you a couple of examples of astrophysical examples where our dead fish has an impact on the measurements or the extrapolation of the measurements that we make. And this talk is essentially on instrument calibration. So calibration, as any truly scientific endeavor, is a collective effort. So there are lots of people behind the results that I'm going to show. I am particularly indebted to these colleagues who have provided me specific materials for this talk, and others whom I'm going to show very soon. So let's start from a very well-known scientific results, which should be familiar to all of you, although I've not seen this picture yet in this conference. Andrea Comastri provided me a couple of days ago with the last version of the spectrum of the X-ray background. And these are the different measurements, a collection of all the measurements of the X-ray background which have been taken so far. Here is energy from a few tens of keV to 300 keV, and here is flux. And the different colors are different experiments. And there are three obvious effects in this picture. There is a scatter in the measurements, which is actually larger below 10 keV than above 10 keV. And there is a systematic difference between the extrapolation of the measurements below 10 keV and the measurements above 10 keV. That you can accommodate by parameterizing the fit, but actually the effect is quite striking. and extrapolation the most recent measurements with respect to the original measurements done by A1 and this scatter is around 10%, this scatter is around 20%. Many of these papers discuss the scientific impact of this uncertainty on the measurements, on the parameters of the X-ray background and the population studies of AGN. And their conclusion is that the 20% different flux between focusing instruments below 10 kV and not focusing instruments above 10 kV implies a factor of 3 difference in the fraction of quantum thick AGN. So it's a large uncertainty that, of course, you can resolve by using different methods to estimate the fraction of quantum thick AGN, like count sources and so on. But these kind of uncertainties, which look small, can have an important impact on fundamental astrophysical parameters. Now, why does this happen? In the literature, you find traditionally 2 explanations. One is very unlikely, that whenever you look, or in general on the average, when you point focusing instruments, you are looking at smaller areas. Non-focusing instruments, they look at larger areas. For some cosmic coincidence, whenever you look at a smaller area, you look at positive fluctuations of the cosmic lines. It's of course very unlikely. So the most reasonable explanation is that there is something in the uncertainties of a calculation of the response function of the instruments which is responsible for this uncertainty in the fluctuations. However, what all these authors point out is that this is a problem limited to the calculation of the response matrix for very diffuse sources, which is more complex than calculating the response matrix for point-like sources. And my claim is that this statement is overly optimistic. Why is that? The first attempt, let's start from the region above 10 kV. The first attempt to try and study in a systematic way these uncertainties on the flux calibration of the instruments above 10 kV is actually a very recent one. It was done by Markus Kirsch almost 10 years ago. And what he did, he compiled all the measurements done by instruments above 10 kV on the Crab Nebula. And this is a summary plot of what he gets. Actually, there are also some measurements below 10 kV, but the Crab is very difficult to measure below 10 kV, except for very old instruments. So if you focus on the measurements above 10 kV, so in this region of the spectrum, this is the NH column density. You are insensitive to the column densities above 10 kV. Here is the normalization, and here is the photon index. And you see actually huge differences. So there is really a large uncertainty, so there used to be 10 years ago, a very large uncertainties in the flux determination of instruments above 10 kV. Now, one of the problems of this plot is that this problem assumed that the Crab Nebula is a power law, and that the Crab Nebula is a constant source. And now we know that neither of these assumptions is correct. Neither the Crab Nebula spectrum is a power law if you cannot be approximated with a power law unless you look at very, very limited energy ranges, which is typically not the case if you have instruments sensitive above 10 kV, nor the Crab Nebula is a constant source. And there is a solution to this problem, is looking at quasi-simultaneous observation. This is a more recent plot provided to me by Lorenzo Natalucci, flux against photon index for 4 high-energy experiments. And still you see that there is a 20% difference in flux between different experiments. So this is a true, genuine problem, which has been confirmed, which has been confirmed also on other sources, like this source published by Fujimoto et al. In brackets, there are at least 2 experiments sensitive in the high energy band in this moment, cuyo nombre no quiero acordarme, to quote Miguel de Cervantes, who coped with this problem a few centuries ago, who use for the calibration of their effective area a specific value of the normalization and of the spectral index of the crowd. So I will tell you which they are privately, but I think this is rather worrying because these are data which are being extensively used and extensively shown in this conference as well. So this is a situation instead in the soft X-rays. Soft X-rays means below 10 kV. What I show in this plot is something with slightly different, but conceptually is the same thing. This is energy, so this is a spectrum in some sense. And this is the flux ratio against the epic TN measurements. 4 different missions, MOS1, MOS2, ACES, XIS, XRT, and NuSTAR. And okay, one is here. So you see that there is, of course, there is an obvious excess of flux measured by essentially all missions with respect to the FPN, but the energy dependence of this difference is rather flat. Actually, these error bars could mislead you because error bars are not really error bars, it's the dispersion of existing measurements. If you want to know when these measurements were taken, there are 5 papers in this web page which actually contain the real measurements. But in general, it is true that above 2 kV, our capability of measuring the spectral shape with the CCD type instruments or with NuSTAR is basically very robust. So there is no strong spectral dependencies as long as you go from 2 kV to 10 kV. Now, that's the situation if you look at the whole band, and actually the situation is much more messy, and what you see that for many instruments, when compared to the PN, there is a short drop of the relative flux below 2 kV. This means that when you measure a spectrum of whatever shape in the epic PN and in the SUSA XIS, for instance, you are bound to get different results in terms of the spectral shape if your statistics is good enough. The annoying thing is that in this region, not all the instruments provide the same answer. So you may wonder who is right and who is wrong, and I don't know. And actually, the fact that we use the epic PN is purely conventional. It does not imply at all that we believe the epic PN is properly calibrated. It's just a relative measurement. So the only statement that I can make by looking at this plot is that we have no idea at the level of plus minus 10%, more or less, which is the flux of the X-ray sources. And that there is a spectral dependency that is also, for which I cannot tell you which is right and which is wrong. Before I go ahead, if I'm not scared you enough, before I go, for the time being, I've just shown you in the soft X-ray band, CCD resolution-like instruments. If I put in the game resolutions, instruments at high resolution, like the RGS, which is this blue line here, or the Chandra gratings, which is all the bunch of plot. This is a similar plot as before, as a function of energy. In this case, Michael Smith et al. In a paper in preparation, they compare the fluxes measured against a common fit. So it's not exactly the same plot as before, but it's conceptually very similar. Once again, if you look at high-resolution instruments, the blue points represents the RGS on board SMM. The black points is the PN, and you see that RGS and PN agree perfectly. And I can tell you they have been independently calibrated. So the fact that they agree is not due that there is a crosstalk between the calibration of the two instruments. But if you look at the Chandra gratings, they behave in any possible way. And once again, the systematic uncertainty on the flux determination is for at least plus minus 5%, and actually in the softest and the hardest energy band is plus minus 10%. And once again, I can't tell you who is right and who is wrong. Now, before I go further, let me properly acknowledge all the persons who are behind this mess, and that actually you should blame for all this. It's not only me here, but it's a whole group of the 40, 50 scientists that who have been working on calibration of high energy instruments in the last 20 years. And since 2006, we decided to work together to try to put this mess a bit in order. So if the situation in this moment looks too messy, you can't imagine how it was 5 years ago or 8 years ago before we started working together. So already the fact that this group has been meeting and working regularly together in the last 7 years has significantly improved the situation. But as you see, there's still lots of problems. We call ourselves International Consortium for High Energy Calibration. We meet regularly and try to discuss to improve the calibration status. Our task is to define calibration standards, publish the cross-calibration status, possibly on refereed journals. And as I mentioned, there are 5 papers already in the literature which discuss in detail the current cross-calibration status and calibration status of all the operational and some past missions. And of course, most importantly for you, improve the cross-calibration. So whenever you have any doubts about the cross-calibration of your instrument, this is the web page to look at. which is, by the way, I'm the person who maintains. So why is calibrating X-ray instruments so difficult? In principle, it's a piece of cake. You know, you have an instrument on ground, you make measurements to depth, you characterize fully instruments with a fully self-consistent physical model of your instrument, and then you will have to make some small correction when it is on flight, but the basic rules are set. That's the theory. In practical terms, for various reasons, which actually our future Athena Plus managers should carefully consider in the future, there is never enough time for ground-based calibration. Some situations are better. Chandra made a quite extensive, even if not completely sufficient, ground calibration campaign. XMM was in this sense much less fortunate. We were actually doing surely not enough ground calibration campaigns, simply lack of time, lack of resources, lack of whatever. In addition to that, the reality is that instruments' performances on flight change significantly due to contamination, due to degradation. So anyway, very often you have to restart the calibration on scratch once you are on flight. And in order to do this, unfortunately, in X-ray astronomy, we cannot rely on standard candle stricto sensu. I've not found any astronomers able to tell me, I know exactly which is the flux and the spectral shape of any astronomical sources of interest for calibration. We have, for many sources, educated guess about the physics of the emission. We actually use, of course, various types of calibration sources like supernova remnants, like galaxy clusters, like isolated neutron stars, like blazars, for which we believe we have an educated guess of which is their astrophysical model. But nobody can actually make sure that the astrophysical model we're using is actually the correct one at the 100% accuracy we would need. So it's a sort of Teufelkreis. So if we want to make astrophysics, we need calibration, but if we use on-flight measurements to do calibration, we need to know the astrophysics. So eventually, what happens in practical terms is the calibration of the X instrument is always with respect to something. So let's see, there are communities actually which are seriously worrying about this because these uncertainties have an impact on their measurements on fundamental fields. And I think apart the X-ray background community I mentioned before, another example is the galaxy cluster community, because these uncertainties have an impact on cosmological measurements. You already know what I'm talking about. We know that the distribution of the masses of galaxy clusters depend on cosmological parameters. You can derive the mass of a galaxy cluster assuming hydrostatic equilibrium, and for this you need X-ray measurements like electron densities and temperature. So the accuracy with which you can measure the temperature has an impact on the cosmological parameter that you derive when you study larger sample of galaxy clusters. Now, how well can we measure temperatures in X-rays? Well, of course, since there is a cross-calibration difference between, for instance, ACES and EPIC, the temperatures that one measures on the same galaxy cluster in ACES, x-axis, and XMM, y-axis, are different. This is an example of a recent sample studied by colleagues in Bonn, 63 bright galaxy clusters. The measurement should be on this line, and actually they are not. The EPIC spectra yield systematically higher temperatures. And the impact on the cosmological parameters is small, but it's not negligible. This is the effect, the consequence of using either XMM or Chandra measure temperature to estimate the cosmological parameter, sigma 8 versus omega matter. And you see that the two contour plots at 60% A confidence level, they overlap, but they are different. Fortunately for the X-ray community, these differences are still much larger than the difference obtained by a different community, the Planck community, when they measure the same cosmological parameters with Planck measurements. So we are not still being shot for this reason, but there are still discussion in the Planck community whether actually X-ray astronomy can be used at all for these cosmological measurements due to these differences, due to these cross-calibration problems. Now, what I would like to show, which is possibly more pertinent to this context, is a glimpse of what these calibration uncertainties may have on measurements more relevant to the topic of this conference. This is a famous, and actually I've not seen it yet in this conference, this is a list of all the measurements of spin in supermassive black holes obtained so far. This is of the order of 20 objects, a usual suspect, a usual bright AGN, local Seyfert galaxies, name, black hole mass, spin, and the references. It's basically all of these measurements have been obtained either with XMM Newton EPIC or with XMM Suzaku XIX data. Of course, we are starting now getting the new star measurements of the spin, but they are not still in this table. So this table stands as the XMM and Suzaku situation goes. Now, since there is a strong and energy-dependent cross-calibration difference between EPIC in XMM and XIS in Suzaku, you might wonder whether these calibration cross differences have an impact, and which is this impact on the measurements of the black hole spin. So I show you two examples. One is a Seyfert galaxy with a spin consistent with maximally rotating, and another one, Swift J2127, is a Seyfert galaxy with an intermediate black hole spin. So what I'm going to show you is how the measurement change if I, just as an experiment, as a thought experiment, change the effective area of one instrument, for instance the EPIC-PN, and I align this effective area artificially to coincide with the effective area of the Suzaku. Actually, when I talk effective area, I should actually say measured flux, of course. But if I change the effective area in such a way that the measured flux are exactly the same in two instruments, in the whole band, between 0.1 and 10. I stress that this is not the case in this moment. This is a thought experiment. So these are the results. I show the results in a plane where on the y-axis there is the black hole spin, and on the other plane the disk inclination angle. This is 630-15, spin very close to what's actually consistent with maximally spinning, and Swift J2127, intermediate spin black hole. And essentially the message to take out of it is that the measurements of the inclination angle is not very much affected, but the measurement of the spin in case of intermediate black hole is affected at the level of 0.1. So 0.1 is the impact on the measurement of the spin of cross-calibration uncertainties of this kind. Oops, sorry. Oops. Right. Sorry for the confusion. Let me allow a very short digression on EPIC, because I've been asked in this conference, and it happens to me every time to all conferences now, how well calibrated is the effective area of EPIC? This is the answer. This is a distribution of residuals against the best fit spectral fitting of 90 radio loud AGN for EPIC-PN, EPIC-MOS 1 and MOS 2. The sigma of the distribution, once the statistical error on the data factor out, is of the order of 1.5% in PN and slightly larger than 2% in the MOS camera. Now, the question which I'm always asked is, well, if this is true, why don't I always get the residuals below 2% in my spectral fitting if I'm sure that I'm using the right model? And the answer is, of course, there are several other effects beyond the effective area which affect your residuals. One of them is the uncertainties in the distribution. This point is actually discussed for the issue of the soft excess in obscured binary in a document, which I invite you to have a look at, where I show, I think convincingly so far, that this soft excess in obscured binary in the most general case is not due to redistribution calibration problems, but I would be happy if you demonstrate me otherwise. And the 2.3 kV feature, so-called, which is a feature of the order of 5% around the gold edge, which is actually not due to the calibration of the effective area, but due to an inaccuracy of the energy scale of the EPIC camera affecting recent observations, for which we know that we know the reason, we have a solution. I would like to take the opportunity to apologize on behalf of my calibration team if the calibration has not been published yet, but it's what happens at some stage in the mission. Either we become lazy, or simply we are not enough to cope with all the work which we have to do. I think it's the latter, but maybe also the former could be right. The energy scale accuracy in the EPIC-PN cameras can be constrained within 10 EV in imaging mode, 20 EV in timing, 50 EV in burst mode. We have different modes in EPIC, which are used depending on the brightness of the source. So the last question I would like to ask is actually the energy scale accuracy also important for the determination of the black hole speed? Otherwise stated, if I have a measurement of an AGN in imaging mode or an X-ray binary in burst mode, is this uncertainty on the energy scale important for my determination of the black hole speed? And this is the answer. On y-axis, I show again the black hole spin. On the x-axis, the error on the energy scale. And I show here the data for two sources, which have been shown in a paper by Walton et al. To show remarkably similar shapes of the broad ion lines. And the punchline, the take-up message from this slide is that the red points, the binary, although the energy scale, the error on the energy scale is significantly larger than in imaging mode, there is no effect on the measurement of the black hole speed. But for the AGN, even an error on the energy scale of the order of 15, 20 EV changes the estimate of the black hole speed by 0.1. So, and this is the same plot for the inclination angle versus the energy scale, and the corresponding systematic error corresponding to an energy scale uncertainty of 10, 50 EV is of the order of 5 degrees. So these are my conclusions. Any astrophysical problem in this moment which requires a measurement of the flux with an accuracy better than 10% is undecided. At CCD resolution, any astrophysical problem requiring measuring features weaker than 3% above the continuum require careful consideration of systematic effects. The current calibration uncertainties at nominal reconstruction of the energy scale is equal. This means for EPIC-PN observation earlier than 1 year ago at the current status of recalibration is at least 0.1 in spin and 5 degrees in inclination angle. And if you want to know more, look at the web page, and if everything else fails, call me. Thank you.
Thank you. Just to tell you that more